Hi, my name is Manish Gupta, and in this video, I'm going to talk about ECLARE, which is extreme classification with label graph correlations. Okay, so let's get started and see how ECLARE works and what kind of problems it can handle for extreme classification area. Right? So let's talk about first the problem of tail labels in extreme classification. So recall that extreme classification is the problem of doing multi-label classification in the space where the label set can be in millions or even more, right? So that's the extreme part. Now, if you look at two interesting data sets, Amazon titles and WikiC also titles, you observe that they have large number of labels, 131K and 320K, making them extreme classification problems. But what is also important is to observe that several number of labels actually have less than 5 data points. Okay, so essentially, if you look at Amazon titles or even WikiC titles, you see that a whole bunch of labels have less than or equal to less than five training data points, less than 5 training data points. Okay, so this basically means that a whole bunch of labels have very small amount of label data of data point to train on. Okay. Now, this basically means that while you're training, it is very difficult to get high accuracy for these tail labels. However, tail labels or these rare labels are actually super important. They basically are the ones that can lead to this concept of serendipity in personalized recommendations, which basically means surprising the user with something really pleasant and something really, really niche catered for specifically for them, personalized for them. Okay. So coming up with good predictions on tail labels is super important. Now, how does ECLAIRE do this? So in this video, I'll talk about the ECLAIRE's algorithm. Let's get started with the first part. So you have to basically embed the documents. You have to also embed the labels and then build some label classifiers, right? So let's see how our documents embedded. So ECLAIRE is a deep learning based extreme classification algorithm and follows the deep XML pipeline, right? So on top of the typical deep XML pipeline, it basically uses the label metadata and not just label metadata like decaf. It also uses the label correlations to perform really well on the tail. Okay. So ECLAIRE contains 4 different components. A text embedding architecture, which will be used to embed both the document text as well as the label text, right? It also learns one versus all classifiers, one per label that will incorporate both the label text information, also label correlation information. Okay. It has a shortlister to make efficient inference and also for efficient backpropagation. Finally, it also learns a label correlation graph, which is basically going to be used to train both the one versus all classifiers as well as the shortlister. Okay, so and it follows the same typical deep XML pipeline, which basically means in the module 1 we'll be learning the embedding matrix in the module 2 we'll be learning the shortlister. Module 3 is going to be the initializer, reinitializer, and module 4 is going to be the main XC solver. Okay. So now just quickly to talk about how the text is embedded. Well, the text embedding in ECLAIRE is more or less similar to decaf, except for an extra parameter here called lambda. Okay. So the way you typically do the text embedding is, let's start from here. So the way you do the text embedding is that you essentially have these tokens xt, which belong to a vocabulary space v. You initialize your embedding matrix by you have an embedding matrix E, and that basically provides you label embedding for every document. Okay? So essentially, you sum over all the tokens T in the document, and that gives you label embedding for not label embedding, sorry, the embedding for every document text. Okay. Now that's the x hat not though, so it's not the final embedding. So to get the final embedding, you're going to take this x hat not, and you're going to pass through the embedding block ed, which is basically this guy, right? And then apply relu on it, and that basically gives you the really the text embedding for the document text. Okay. Now, essentially, the way you do this embedding ED is using this block where, after you get this x hat not, which is basically going to be set as V here, you essentially pass that to a ReLU and then multiply with the D cross D matrix R, where D is the dimensionality of, of the vector x hat not, right? This is also D-dimensional in that senses. Okay, so you pass through R, and then you apply, you have a weighing factor lambda, and this is basically the way residual computation is done. Okay, so that basically gives you the overall. That gives you this embedding block output, which is, you apply relu on top of it, and that gives you the document text embedding. So that's how document text embedding is computed. This xt here is basically, of course, the representation for the token T, and it's actually the TF-IDF weight of the token T in the document I. Okay. So that's that. Now, of course, this entire embedding essentially has two parameters to learn, which is R and then in lambda. And of course, you also have your embedding matrix E. Okay, so that's basically those three things to learn while you are trying to get document text embedding. Okay, so that's that. Now, ECLARE also has this notion of label correlation graph. So essentially, for tail documents, as we noticed, tail labels, sorry, as we noticed, you do not have too many documents, too many data points that are connected. And therefore, you can enrich the information about those tail labels by doing label correlations, right? So that is why ECLARE uses them. It uses document label associations taken from the ground truth to infer indirect correlation between labels. Okay. So for example, let's look at this. So this is a small part of the graph. You essentially have, it's a bipartite graph. So essentially you have the labels on this side and you have documents here, right? So you have Anatolian Shepherd, Sarabi Mastiff, and so on. Those are the documents and you have labels on the right side. Okay. Now, this is the ground truth labeling, which basically means that if you really think about it, Tibetan Mastiff, for example, is a tail label. It just has one document associated with it, right? Similarly, Bully Kata has basically two documents associated and so on. Okay. Now, the way label correlation graph is learned is basically using random walks in ECLAIRE. So, if you do not know random walks, just search for some primer on random walks, right? So it's actually pretty simple. The way random walks are done is basically you take this graph, you start from every label node, and for every label node, you do several random walks. In fact, the way you do random walks is as follows. So here, basically, we show the random walks for starting from this node Kangal dog. Okay, so you essentially start from there, and with a particular probability, you move to any of the connected nodes. So basically, here there is only one connection, so you're always going to move to Anatolian Shepherd, but you randomly choose a neighbor, and then you go to the neighbor. With the 20% probability. Okay, with the remaining 80% probability, you just restart. Okay, so you just restart another random walk. Okay. Now, how many random walks will you do from every node? Well, you keep doing it. Until you have a limited number of random walks. You don't keep doing it forever, but you restart 80% of the times, and essentially 20% of the times you follow a random edge. Okay. So random walk length is 400, so you do not do too many and too long. I mean, well, 400 is quite longer random walk, but that's the hyperparameters that they found to be the best. So these are random walk hyperparameters, not really learned, but just tuned and fixed. Okay. So in this particular figure, you see two random walks, the red random walk and the green and the blue random walk. Okay. So different colors actually denote distinct restarts. So that's that. Now, essentially, so originally, if you looked at this node, Kangal dog, it will be associated with only two different labels, this Apkash dog and this Aksarai, Malak C dog, right? But then, thanks to these random walks, you're able to actually get correlations with more labels, this Bully Kutta and Tibetan Mastiff, right? That basically gives you more correlations with more labels, basically densifying the label correlation graph. Okay. Now, so that's that. Now, while doing this, what could happen is that if you really look at head labels, they are connected to too many other nodes, which basically means the head labels can easily overwhelm the rear labels. And therefore, before doing these random walks, they do two main steps. One is to disconnect head labels or torso labels from the entire graph, so as to give more opportunity for the random walks to pass through rear labels. And also, they basically favor edges to or from rear labels rather than to or from head or torso labels. Okay, so that's that. Now, so we've understood how label correlation graph is created. We'll call this label correlation graph as G. Okay. Now we will see how this label correlation graph is used to learn good label embeddings. Okay. So label embeddings are learned in ECLAIRE in three important ways. Okay. So we'll look at these three ways on this slide. Okay. The first simple way of learning label embeddings is to basically just learn label text embeddings, as was done in DCAF. DCAF, the main selling point in DCAF was coming up with label metadata or label text embeddings. That's what ECLAIRE also does. So the first step is effectively just take all the labels which are there as part of the label text, all the words which are there as part of the label text, multiply by the embedding matrix E. This is the same embedding matrix that you also used for for computing a representation for document text. Okay. So that gives you your ZL naught, and then you pass through an embedding block EL, so as to basically get the first label representation called as label text embedding or LTE representation. That's great. That's the first representation. Um, the second representation, or let me first talk about the third representation because that's easier. So just like decaf does, they also have a refinement vector ZL3, which basically is randomly initialized and learned over the learned while training. Okay, so that's the refinement vector that you would learn, and a representation that you learn for the label. Okay, of course the refinement vectors are per label, so essentially that's your ZL3. So that's your ZL3. Which is basically shown here. So it's not obtained from anything specifically, just randomly initialized. OK, so your ZL1 is basically obtained using your label text. So of course, you will ignore the stop words and you get the label text. You basically get ZL1. OK, now how is your ZL2 obtained, which is basically the third label representation? OK, it's obtained using graph, using the label correlation graph that you learned. OK. So it's basically called as graph augmented label embedding. So it's basically graph based label embedding. So that's why it's called graph augmented label embedding. Okay. So now notice that you essentially have your labels, and you have essentially already obtained your label representation for every node. So this is basically the same ZL hat knot. Okay, we're calling it ZM hat knot because M is just another label. Okay. So the way you do this is to first build, of course, the label correlation graph. So G, you have the label correlation graph G, and you want to basically learn a better embedding for a label by doing a GCN, graph convolution neural net, on top of this label correlation graph. You just do one layer of GCN. Of course, ECLARE does one layer of GCN, but they also say that you can do K layers of GCN for that matter. Okay. So if you basically remember GCNs, they contain two main operations, the graph convolution operation and then a transformation or the graph pooling operation, as they call it. So there's no pooling that happens here, it's just a transformation that is happening here. Okay. So the graph convolution, the main idea is to basically look at neighbors and then come up with the revised embedding for the node based on its neighbors, which is what is happening here. So for any label L, you're basically going to look at its neighbors M, and then neighbors, the similarity between neighbors is defined by this graph, and then you learn a representation for the label L based on the representations for these neighbors. Okay. So of course, while considering these neighbors, you can also consider the self as a neighbor because your label correlation graph would have computed a self weight as well. Okay. So and then you do transformation. So this transformation is again done using the same embedding block. So that's a reuse of this interesting embedding block. And then that gives you your ZL2. Now, once you have your ZL1, ZL2, and ZL3, all three of them, right? You basically do an attention. So you learn how much weightage to give to each of those representations so as to learn your final classifiers. Okay. So as to be able to do that, so you have the attention block A, which is basically shown illustrated here and explained in the equations here. So you take these three representations, ZL1, ZL2, ZL3, you pass them to ReLUs. So you pass them through ReLUs and apply a transformation T on top of them. So that gives you, after that you apply a sigmoid, that gives you your T of X. Okay. So you basically get T of ZL1, T of ZL2, T of ZL3. So forget about the K here, K is just one. So you get T of ZL1, ZL2, and ZL3. Okay. And that basically, once you get those, you basically call it QL, the large query label, query vector for the label L. Of course, you get it for every label. Remember, each of those ZL1, ZL2, ZL3 are subscripted with L, which means they're specific to a particular L. Right? So, and then you basically compute the attention weights by multiplying, by randomly initializing this vector A. So weight matrix A. So, attention is, the attention variable is, of course, learned over iterations, and essentially you have your Q. So you have A, you multiply by Q, and then, essentially you compute the attention weights. So you get attention weights alpha L1, alpha L2, and alpha L3 as is shown there. Right? For generic cases, when you essentially consider multiple K different layers of GCN, you basically will have the K that is basically being shown for generic for generalization in these equations. But in general, ECLARE just uses K equal to 1, right? K is set to 1 in ECLARE. So therefore, you have like alpha 1, alpha 2, alpha 3. You use these alphas so as to essentially get your final WL by doing a weighted addition. Okay. So that's how label embeddings are obtained in ECLARE. Okay, now shortlister. How does shortlister work in ECLARE? So shortlister works more or less the same as in DCAF, except for something called as gamification, and therefore we'll talk about that. Okay, so what is shortlister meant for? Well, if you basically didn't have shortlister, then at train time you have to basically backpropagate through all the labels, and at inference time you have to essentially compute the similarity between the embedding for this data point and all possible labels, label classifiers, right? So that's too much of work and that's compute intensive. Therefore, you use shortlists, which basically bring down the overall computation time from O of L to O of log L, right? Of course, other factors remaining the same. Okay. So what is a shortlist? Well, if you have seen my previous videos, you already know about the shortlist, but it's basically O of log L negative training point, negative labels per data point, right? So at train time, they're training points. At test time, they are just candidates of which you want to evaluate and rank, and then figure out which ones are correct, which ones are relevant. Okay. So just like decaf, ECLARE also uses clustering-based shortlister. So essentially, it uses a balanced partitioning of L labels into K different clusters. So K is typically 2 raised to 17, right? You will also call we also call these these clusters as meta labels, and then you essentially solve the meta XC problem of learning classifiers, one versus all classifiers for each of those labels, meta labels, right? Meta labels in that sense. Remember, the labels could be too large, but meta labels are 2 raised to 17. Okay, that's not very, very large. Okay. Now, so overall in clustering, you basically obtain these clusters C and also the one versus all classifiers H for each of those meta labels or clusters. Okay. Now at train time for a data point, you basically are going to do the beam search over this balanced tree, and you're going to figure out the best matching B clusters. So with the highest scores. So basically you compute the scores using those cluster one versus all classifiers, and that is how you basically get the cluster scores. So typically one would say that yes, these clusters basically give you labels. So all the labels in these clusters can be considered as part of shortlist. So that's what decaf does. Now a game does something, ECLARE does something more beyond just this. So it essentially expands on these B clusters so as to essentially get a different set or expanded set of clusters. The way it does it is basically called as graph-assisted multi-label expansion. Okay, so it expands these clusters set using game graph assistance. Okay, so how does it do this? So basically you have your scores, and remember these are scores per cluster. Okay, these are still not label scores, these are cluster scores. Okay, so you have like p hat, p tilde, which are basically cluster scores. You multiply this with m transpose gm. What is m transpose gm? G, as you would recognize, is your label correlation graph. M is your cluster assignment matrix. It basically just tells which label belongs to which cluster, and therefore M transpose is basically the transpose of the cluster assignment matrix. Okay, so that basically gives you a revised set of clusters P. Okay, and then you could basically choose the top B clusters from this P, where B they basically set to 30 to 50 clusters, and all the labels belonging to these clusters are now your candidates at inference time or basically negative label suppliers at train time. Okay. So, now, so at inference time, what happens? Well, at inference time, so this was all train time on the left side. At inference time, what happens is shown on the right side. Okay, you basically get a document X, you get the document embedding, and that gives you a document embedding. You use a shortlister S so as to essentially get a shortlist of top B clusters. And they also come up with their scores P. So the same P that we talked about right there, right? So same P. So essentially, they get their scores. Now, and then from those P at inference time, by the way, from those P, you get the labels. Okay, so you basically get all of those labels and rank those labels so as to essentially obtain a ranking over the labels. So label 3, label 11, label 7, label 9, label 14, label 1. You're basically going to use the classifiers for the labels WL. Remember, WL are the label classifiers. They are not the meta label or cluster classifiers. So the label classifiers, use them, and then you get the label ranking scores R tilde. Okay. Now at test time, you do not gamify the clusters. Instead, you gamify the labels. Okay. So the way you gamify the labels is that you have R tilde, which is essentially, essentially in the label space, you multiply that by G. Remember, you don't multiply this one by M transpose GM, but you multiply that by G, which is a label correlation graph, so as to get gamified label ranking scores R. Now, so remember, R tilde is basically a vector of the size of the number of labels. G is basically a matrix of label cross label matrix, and R therefore is going to be a label sized vector. It's just a ranking vector across all labels. Okay. Final predictions are not just done by R; they are actually done using R multiplied by PM. Okay. So essentially, for every label, the final score is going to be its label ranking score multiplied by the meta label cluster score. Okay. Okay, so that's basically more or less ECLARE, right? So ECLARE, of course, follows deep XML pipeline. So essentially, it has 4 modules. In the first module, you are going to solve the meta-XE problem with K clusters, again, balanced hierarchical binary clustering. The more important thing is that for getting label embedding for this module 1, you do not use refinement label vectors. Remember that ZL3. So ZL3 is not something that you're going to use. Sorry, ZL2. ZL2 is something that you're not going to use. The third label embedding because you want to motivate good learning of the embedding. So of course, always in deep XML pipeline, the goal for module 1 is to learn the embedding matrix E. Okay. So clearly you also jointly learn many other things, but then those are just there for the sake of it. You delete them after everything is done. Just retain E. E is what is passed on to the next module. In module 2, you essentially don't. So in module 1, you basically use very simple representations of the label. Essentially, all you do is this. Sorry, you don't even do this, right? So in module 1, you basically just compute the representation of label as summation over xi's. Where you consider all of those where so label representation is learned as a bag of words representation over all the words contained in those labeled texts, right? Or you could basically look at aggregated representation over words in the documents. Okay. But in module 2, just like in decaf, you basically also do this. You essentially have the embedding matrix, which has been learned from module 1. So you use that. But you do one more interesting thing. And the interesting thing that you do is to enrich these label representations using the graph correlation, the label correlation graph that you have trained as part of module 1 itself. Okay. So in module 2, you essentially use these as your label representations. And of course, you basically create centroids and the entire, K clusters and so on, hierarchical binary clustering. You solve the meta-XE problem and you learn shortlister S. Okay. So that's the goal for module 2, learning the shortlister S. Now in module 3, you basically freeze E and S. E learned from module 1 and S learned from module 3. Of course, you reinitialize everything else. And you also initialize the refinement label vectors, which you had ignored in module 1, but you initialize them using the embedding matrix. So using the embedding matrix, you take the Z representation of the representation of each of the, this is the label text representation of each of those labels. You multiply by GM, of course, considering all the neighbors M for a label L, and that gives you your initialized embedding ZL3. Okay. So module 4 is going to be your main XE problem solver. And on the way, you're going to learn, of course, other things, but the main thing to learn is the label classifiers WL. Wherever you have, wherever ECLARE does learning, it uses binary cross entropy loss and spectral regularization for all the matrices that it learns. Okay. Okay, so how does ECLARE perform? So ECLARE performs way better compared to several other XE methods, as observed on multiple public data sets in terms of PSP, precision, and recall. So it performs to 3.5% higher in terms of precision at 1 and up to 5% higher in terms of PSP, 3% higher in terms of recall. If you also look at quantile-wise plots, which basically tell you in different buckets as to how these methods perform, different buckets in terms of labels. So each bucket has same number of labels. So bucket number 1 is the head label. Bucket number 5 are tail labels. Of course, this one is the complete test set. Okay. So what do you observe? You basically observe that ECLARE actually not just improves on other algorithms, but improves really well on the tail labels, which is super important and which is what we started off from. We want really good performance on tail labels, and which is what ECLARE has been able to achieve. Now, here are some qualitative examples. So if you basically see WikiC also titles dataset for the document Tibetan Terrier, ECLARE has been able to come up with really good labels. So those which are highlighted in black, dark black, or in dark text are essentially ground truth labels, while other methods come up with some labels which are not ground truth labels. So they are actually not so precise, right? So essentially, in fact, what is super important to notice here is that ECLARE was able to come up with this label called as dog of Osu. And this label actually just occurred twice in the entire training set. So it was really, really super rare label. So ECLARE is able to get rare labels also. If you look at the other example, 85th Academy Awards, other baselines essentially are stuck with this phrase Academy Awards and therefore come up with other other labels which are different versions or editions of the Academy Awards, or with labels which have to with other entertainment awards like Primetime Emmy Awards and so on, which have to do nothing with Academy Awards, right? But ECLARE is able to come up with the really relevant and also diverse set of labels here. Okay. Now, ECLARE's awesomeness is basically because of the use of label correlation graphs. Now, label correlation graphs were also used while doing the shortlisting, right? So even in the shortlister part, right? And basically while creating those clusters and so on, the embeddings that are trained in module 1, thanks to label correlations, are really good embeddings. And that basically leads to really good clusters. So if you look at the clusters learned by DCAF or clusters learned by ECLARE, you basically observe that in general in ECLARE, clusters are much more coherent. They are basically labels which are really relevant to each other in that senses. Okay. Okay, in summary, in this video, I talked about ECLARE, which basically goes beyond decaf and incorporates label correlation information. Okay, ECLARE basically uses label correlation by first creating a label correlation graph and then doing a layer of graph convolution neural network on top of it. ECLARE follows a deep XML pipeline, so it therefore does label clustering, negative sampling, shortlisting, and re-ranking. You can try out the ECLARE code there. That's it for this video. Thank you for watching. Connect with me on my LinkedIn or look at my research on my homepage. Thank you.